Good afternoon, Professor Valent and Professor Bellet. We welcome you here in this GAN course on functional material.
Hello.
Hello.
Hello, shall we start now?
Yes, sir. Yeah, we can start, sir.
Okay. So good afternoon for the evening session for you. For me, it's afternoon session anyway. So now today's tutorial will be somehow continuation of the yesterday's. Yesterday, Professor Fanetti was talking about electron microscopy. And today, Dr. Belets will introduce you many other characterization techniques that are used to fully characterize particular materials. So he will take you through the whole lecture, and I would like now to invite him to start the lecture, and also want to ask if you can allow him to share his screen.
Sorry, yes, sure, sir. Yes, sir. So he can present now.
Thank you. So now you see the presentation. Okay. So hello to everyone. I'm Dr. Belets. I'm the researcher and assistant professor at University of Nova Gorica. I also teach the course instrumental methods in environment, and a little bit of this I will present you also today. So first of all, what is material? So according to the English Cambridge Dictionary, this is a physical substance, the thing or things that can be made from, and what we can touch, see, smell. So basically everything around us. And so the material got physical or chemical properties. So physical properties are those that is measurable, whose value describe a state of a physical system. So as, for instance, density, melting point, thermal conductivity, electrical conductivity, corrosion, and so on. On the other side, we got chemical properties of those materials. So those are properties that becomes evident during or after a chemical reaction. So we cannot see it or view it, touch it, this substance when it goes some change of chemical properties, but we see the result. So this is some heat of combustion, enthalpy of formation, chemical stability. So this we can also indirectly measure. So why we have to develop, or we want to develop new materials? I think these two images are more than enough, because we can see it at the beginning. We got those big bricks of mobile phones, and then they are going smaller and smaller, and today they are again big, but we got basically the computers in our pockets. The same is with microprocessors. First, it was silicon transistor. Now we got really small and very powerful processors that can store a lot of information. Also, can produce, calculate lots of information. So when we develop some new material, we don't know it immediately if it's good or bad. So first, we have to think it in the why we want to do new material and why. So what or which property we want to change to observe it, what we want to improve. The next is then if the material is solid, liquid, gaseous, stable, not stable, crystalline, so on, in which state of matter it is. And then we somehow do a plan, so some hierarchy to characterize it. First, when we synthesize something, prepare, we need to know its composition and for sure the purity, if it's pure or we got some side products also involved in our result. Then we need to know its morphology, crystallinity, and at the end also the physical and chemical properties. But after that, when we got this plan, we have to choose the right method to detect, measure, or evaluate the above mentioned properties. And today I will just introduce some basic principles and basic methods that are used in the process of developing new materials. First, we will go through the spectrophotometry, where I will present you atomic absorption spectroscopy, emission spectroscopy, UVVs, and ER spectroscopy. Then we will head out to the mass spectroscopy. And after that, separation processes, where we will focus on chromatography, and then thermogravimetry, and at the end, X-ray analysis. So the methods, the most used methods where we use X-rays. I will not talk about the microscopy because, as Professor Warland already said it, we had microscopy yesterday. The basic literature regarding this course, and also I would say it like a Bible to the holy book about the instrumental methods and instrumental analysis is Principles of Instrumental Analysis, 6th, 7th edition, or even older, so written by Cook, Holler, and Crunch. So as I said at first, we will I will present you the spectrophotometry. The basics, basics of spectroscopy. We know that spectroscopy is any procedure which uses the interaction of energy with matter in order to identify or estimate the analyte. So in this spectrophotometry, we use electromagnetic radiation to analyze the samples. Here we got the well-known image about the spectrum of where different electromagnetic radiations are like positions. So at which region we can find different electromagnetic radiations. So at the beginning, so at smaller nanometers, if they are X-rays, then we are going to the ultraviolet, infrared, and then heading to the terahertz and radio wave. And in each region, so each region can be used to identify different properties, so to measure different properties. So electromagnetic radiation, this is light, radiant heat, gamma rays, X-rays, UVs, and so on. But it's very interesting that it has the dual nature of light. So it can be described in terms of both of waves, so sinusoidal mode, or particles, so stream of discrete particles, photons. If you remember, Albert Einstein was also wondering about this and described that sun gives the radiation that is not just waves, but it also can be particles. So when we describe the radiation as a wave, we have to deal with three basic terms. First is wavelength, so distance from one peak wave to the next. So this is one wavelength, so from one to second peak. Then we got also amplitude, so how big this wave it is, so from the plus to the 0 and to the other, so from 0 to minus. Then we got frequency. This is number of peaks that pass a given point per second, and wave number, so number of waves per centimeter. When electromagnetic radiation interacts with a sample, it gives different results. The main are three results, so the basic three interaction. So first is the most known, also the absorption. So when incident radiation interact with the sample absorb this this energy, and it goes from the stable state, so from the ground state to the excited state. And then we measure this energy that it was needed that the material went from ground state to the excited state, and we got the spectrometer. Of course, we can then also measure how much light passed through, so this is the transmission. The second one is emission. So again, when the energy comes to the material and interact with it, the material will go to from a ground state to the excited state, but compared to the absorption, here we measure the energy that is needed that the material goes from the excited state to the ground state. And the last one is the scattering, when incident radiation scatter around, so scattered from the material, and then we measure this energy. So those are just important terms that we use in the in these fields, so absorption, transmission, absorbance, and so on. So for your knowledge, in the spectroscopy, we have to distinguish between two poles. So if we measure atoms or molecules, basic principles are the same. So we got emission, absorption, and scattering, but there are differences in the spectrums also. So when we are dealing with atoms, we get well-defined lines. So due to the small number of possible transitions, as we can see it here, for sodium vapor, we got really defined lines. But when we got the molecules, this is more complex structure. Of course, it's built from the atoms, but here we got many atoms and also the bonds between those atoms. And then we have to also think about the energies of vibration energies between the bonds, electronic energy, rotational energy, vibrational. And we get quite complex spectrum compared to the atomic absorption. And for instance, if we got the mixture of molecules, it could happen also that some peaks can overlap, and analyzing such spectrum is very difficult. As I said it, when we are dealing with the atoms, when the energy reacts or interacts with the atom absorbs photon, electron, and it goes from the ground state to the excited state. So this is the only transition when we are dealing with atoms. But with the molecules, we get the additional energies that are connected to the energies between of the bonds. So, for instance, this is one of the presentations, how many transitions we can expect in the molecules. So there are the energies from electronic energy levels, vibrational energy levels, and rotational energy levels. All these energy levels are connected to the bonds between the atoms. So we can see, so we can detect the energy between the sigma transition, N to sigma transition, or N to P transition, or P to P R state transitions. So as I said, the first topic was spectrophotometry. The basics here is that we light the sample and then we detect what it comes out. So of course, at the beginning, we have to have some light source, then wavelength detector, which select the light that we want to detect, so that we want to pass through the sample. And we got our sample, light detector, and of course the computer where our result is, it can be observed. The majority of the photometric spectroscopy techniques based on the measuring the absorbance and transmittance. Here we can see that the transmittance is a ratio between the incident light that comes to the sample and the outcoming light. It is expressed in the percentage of light that pass through. And of course, it is connected to the absorption. So absorption with this equation. But at the end, here we can see that it's also absorption connected to transmittance and to the Bernoulli law, which tells us that absorbance is directly proportional to the path length that incident light pass and the concentration of the absorbing species. And so different molecules absorb radiation of different wavelengths, and then the absorption spectrum will show a number of absorption bands corresponding to the structural groups within the molecule. So with the Bernoulli law, we can calculate the relationship between the absorption and the concentration of analytes. So with this, we do it the quantitative analysis. As I said, so these were the basic stuffs of spectrophotometry. So Bernoulli law, it can be applied for atomic absorption and molecular absorption spectroscopies, but when we are dealing with molecules, it gets more complicated. I will present to you a little bit later. The first method regarding this spectrophotometry is optical atomic spectroscopy. So it is the study of electromagnetic radiation which is absorbed and emitted by atoms. First condition is that the elements present in the sample have to be gas, so they have to be burnt and they have to be in gaseous state or to be in elementary ions. This we can achieve with the atomization. And it is this method is appropriate for liquids and solid samples, but depending on the sample, we use different atomizers. So to gas the atom, gas the sample. So atomic absorption spectroscopy was first used or came into the practice in 1955. It was used for detection of metallic elements. We can quantify over 70 elements, and it's based on the absorption of light of the atoms. So when they're going from the ground state to the excited state. This method is highly specific and high resolution methods because atoms, as I said before, got really narrow characteristic absorption lines. This goes to the 0.02 to 0.005 nanometers, and accuracy is 1 to 2%. So atomic absorption spectroscopy is analytical technique that can measure the concentration of elements. And of course, first we have to detect them. So it's quantitative and qualitative analytical methods. So just to remember, the basics are that we got some incident radiation, the sample which is now at the ionic state or atomized, atomized, and then we measure the energy that is needed that those atoms or ions are going from the ground states to the excited state. This is the basic atomic absorption spectrometer, where we got our sample. It should be, usually it is dissolved in a solution, or it can be even solid. Then we introduce it here behind this atomizer, which is which atomizes the sample, and the sample is going to the flame. From the side, we got the lamp that chooses the and monochromator that chooses the light that passes through the flame, and on the other side we got the detector. So this is the sketch of this spectrophotometer. So the sample is introduced to the evaporator and then goes to the flame. We got hollow cathode light bulbs, and which produces the light that goes from through the flame and to the monochromator. The monochromator can be in front or behind the flame, and at the end we got the detector and the computer. So the requirement, as I said, are that the sample has to be introduced into the excitation source in form of the solutions. This is the most common way, most commonly in aqueous solution. So disadvantage of this method is that many materials have low solubility in common solvents, especially in water. So we in this case, we have to have extensive preliminary treatment. So prepare the samples to the right form so it is soluble in the common solutions, so that we prepare the solutions. In this case, we can face some difficulties. So because we need to use high temperature, strong solvents, we have to also use some really strong acids or base combustion techniques, and everything mentions. With everything mentioned, we risk that we lose the analyte in the sample, or even that the analyte react under such strong conditions. But the advantage is that in modern atomic absorption spectrometers, we can also introduce some materials directly, so that are semi solid or semi hard, as for instance blood samples. Then we can directly also introduce petroleum products, organic solvents, plant leaves, and so on. The opposite of the atomic absorption spectroscopy is atomic emission spectroscopy. So it measures the radiation emitted by the excited atoms. If you remember before in atomic absorption spectroscopy, I showed you that we got the light bulb in front of the flame. Here we don't need it because we don't measure the absorption of the incident light. So the temperature of the atomizer, it's big enough to atomize the analyte atoms and excite them. Of course, depending on the sample, we have to choose the right atomization process. So if we got the standard gas flame or we got plasma flame, with emission spectroscopy, we can analyze approximately 60 elements, for they rely on the emission lines. It's very high, it's high specific and high resolution method, but it's expensive due to the optic that is installed into the machine. Also, the problem is that we got a large number of lines compared to the absorption spectroscopy, and here we got the problems of overlapping, especially if we got mixtures of atoms in our sample. And so to remember, so that atomic emission spectra compared to the absorption does not measure just the light, so the energy that is needed for excite the atom, but we measure the energy that is needed to go to the ground state. So now we already come to the optical molecular spectroscopy. So here is molecular spectroscopic method based on the interaction of molecules with electromagnetic wave. So here we got different methods. So UV-Vis method, ER and NMR. So result also depends on the wavelength, so on the energy in which region we observe or perform our analysis. I would like to note here that term molecules that not only defines like organic molecules, we can also identify or measure inorganic particles, organic molecules, ions, non-soluble complexes, and so on. Even the atoms, but as I will talk about it later, we have to prepare them properly. So usually we need to complex them in some insoluble complexes. So the basics of the basic behind the spectroscopy, it's again Berlin-Bell law. But as I said it before, behind what we are measuring is not depending only on the excitement of each atom, but we have to take into the consider also the energies involving in the that are happening between in the bonds between two atoms. So molecular absorption spectroscopy usually measure in UV-Vis or some instruments also in the ER range. And the most common method is, of course, UV-Vis spectroscopy. So as I said it before, Berlin-Bell law is a sacred law that also applies not only for single phase system, but also for the mixtures. As we are seeing here, this we got then the total absorption that is connected to the each constituent. So for instance, each molecule, each in our sample or each fragment of the sample. But however, we got some limitations of the law. It only applies for absorption behavior of media with low concentrations. because at higher concentration we can it can happen that we get solute-solvent interactions, solute-solute interaction, hydrogen bonding, sedimentation, and so on. So with higher concentration, we got also smaller intramolecular distances, and each particle affect as charge distribution of its neighbors, and we get false result. Or for instance, if we got that the sedimentation occurs if we are visualizing that molecular spectroscopy methods usually uses some cuvettes where we put our sample inside, and if we got the sedimentation occurring in our sample, we don't have the right result because at the beginning we got homogeneous sample distributed all over the cuvette, and we got incident beam passing through. But usually the method is not instantaneously, and we have to measure it for a few minutes or even longer. And then our sample sedimented, and the measurement at the beginning and the end, it's not the same. And we got the false result. So as I said, it's the most common method for molecular spectroscopy is UV spectrometer. At the beginning, we got a source of light, different lamp, deuterium, tungsten lamps that passes through the monochromator, which uses the light that pass through the sample. Then the light passes through the sample, absorb the electromagnetic wave, and we measure then the transmittance, and according to the Bernoulli law and the connection to the absorption, we can get our concentration, and also we get our spectrum. Usually the spectrophotometers also got the reference cuvette inside and also the beam splitter. So our result already does not contain the spectrum of the background, but is already subtracted. So we got the pure spectrum of our sample. Modern spectrometers also got this special feature. So diffraction gratings is an optical component with a periodic structure, as it is presented here. This part of the instrument splits and diffracts light into the several beams, so we can also measure at the specific wavelength. So as I said, the most important part of the spectrometer is, of course, light source of the spectrometer. As we see it here, we got different sources of the light. So deuterium, tungsten, xenon, light-emitting diodes, and as you can see it, they produce spectrum in different wavelengths. So we can measure our sample in the different ranges. Of course, we have to know it where we expect the peaks of our sample. For instance, with tungsten filament lamp, we cannot detect some peaks below 500 nanometer because we got the minimum. But with the deuterium hydrogen lamp, we can observe it because around 200, a little bit above, we got the peak. So because of that, we need to also know the specification of the lamps. If we need a different lamp that is already installed, we just change it, or some instrument also already got different lamp installed inside and just choose the right one for our sample. So with UVB spectroscopy, we can quantitatively and qualitatively analyze really broad spectrum of materials. So from ions, organic species, inorganic species, complexes, so on. So here below, we got some presentations what we can measure. For instance, those are UV spectrometer from Earth elements. You can see that we got a lot of different absorption peaks compared to the transitional metals where we got just one peak or maybe two peaks. Even here, different atoms got different absorption peaks. On the other hand, side, those two spectrums are from inorganic particles. So inorganic nanoparticles can also absorb light in different wavelengths. And we can see it, for instance, HT, this is hydrothermally synthesized particles that got really broad absorption range to from 300 to 800 nanometers. On the other hand, the same particles will be the same composition, but coated one, we get a different spectrum. Also here, those are the same particles that are presented in this left spectrometer, but doped. So we change a little bit the composition, and we can see that the UV spectrum is quite similar to this of hydrothermal synthesis, so no coated particles. So with this method, we can also observe how the optical properties change with if we coat some materials or we change their composition and so on. On the other hand, of course, we measure the organic compounds because all organic compounds are capable of absorbing electromagnetic radiation because they contain valence electrons that are excited, and most application of absorption spectroscopy to these compounds based on the transition from N to P. And here is the presented table for different organic compounds and also where we can expect the peaks, absorption peaks, and which transition is responsible for this absorption. So the second most known and most used molecular spectroscopy method is infrared spectroscopy. So ER absorption, emission, and reflection spectra we can obtain for molecular species, and those spectra arises from various changes in the energy regarding the transitions of molecules from one vibrational or rotational energy state to another. So we got in ER spectroscopy 3 different regions where we can measure in these different regions we can measure different samples. For instance, solid or liquid materials can be measured in all 3 regions. For instance, just complex liquids or solids can be measured in a mid-ER region. Also, what we can measure, so measuring types or reflectance, absorption, or emission depend on the sample and on the spectral region. As I said, in the ER spectroscopy, we are measuring the energy of vibrations, so vibrational modes in the molecules. So molecule can vibrate in different ways. So it can bend, symmetrically stretch, or asymmetrically stretch. rotate or even go up and down, so translation. And even and these energies we can measure with ER spectroscopy. So we measure it above this. So UVVs, it's ER region. The most known and most used spectroscopy is FTER spectroscopy. So Fourier transform infrared spectroscopy. Why FT? Because it transformed the signal from the time domain to its representation in the frequency domain. So the maths, the physics behind it gives us better results, so resolution. The advantages of the FTER spectroscopy over the other ER spectroscopy are that we get very good signal to noise ratio over the most mid ER spectra. We got better signal in order of magnitudes to the older ER spectroscopy methods. So optic enable larger energy throughput, and because of its better optics and incorporated with combination of the maths, so the physics of Fourier transform, it goes. We have also high resolution. We can measure high resolution spectra for gases mixer with that gives us complex spectrum. So this means that we don't have the overlapping of peaks. We can also study the samples with weak absorption bands, so catalytic surfaces, or we can even study the kinetics of some molecules. For this analysis requires small quantity of sample, and it also can measure reflection, spectra, and emission, not only absorption. So this is the representative ER spectrometer. As we can see it, we got different regions that tell us different informations. So for instance, in the high wave number region, we got single bond stretch, then we got the triple bond stretch, double bond toward the lower, and at the end, we got the fingerprint region is from 1,500 to 500 centimeters. Of course, we don't need to know all the wave numbers and all the positions of the peaks. Because of that, we got the libraries, and just we need to know what we expected, and then go to the libraries, or and we see the see and find the right wave number that corresponds to which stretch, and so on. And according to this, we can also then determine our molecule, so the structure of our molecule. So with this, we end the spectrophotometry, and we will head to the mass spectrometry. Here we don't have any light of source of light for analyzing the samples. So what does mass spectroscopy do? As the name said, it measures mass better than any other technique. It was developed for this. So it can give you the information about the chemical structure or composition of the sample. So with mass spectroscopy, we can identify very far quantitatively detect the elements, drugs, peptides, synthetic organic chemical polymers, basically everything. Basically every material. So mass spectroscopy is very powerful technique in the analytical chemistry where that is used to identify unknown compounds to quantify known compounds. So I will present you a little bit later how it works. So, but from putting together the fragments, known fragments that we can get from the spectrogram, we can build up our unknown compounds. And so therefore we can allocate the molecular structure. So it's the analytical technique that use to measure the mass to charge ratio for the ions. So always you will see this M to Z ratio in the spectrometer. So as I said, application is first initially it was used to identify the isotopes, and now is the powerful tool to calculate and determine the molecular masses of atoms, fragments, and so that we can characterize our new compound. Our fragments, so our results we measure in the atomic mass units or daltons. And if we use inorganic samples, for instance, we can also measure it in grams per mole. Basically, the mass spectrometer is a fancy word for high precise analytical balance, because we really measure the mass of ions. As we can see it here, the comparison, the analytical balance is really good. They are going up to 1 milligram, 10 to milligrams, up to 1 grams. But mass spectrometers, they are going to minus 24 grams to minus 19 grams. So it's really high precise analytical balance. So how it works? It works so that we got some inlet of our sample that should goes to some atomizer, ionizer, where we transform our sample into the ions. Then the ions go to the mass analyzer, which is the usual is like such horn, where the ions come inside and they bounce it around this tube. So we got the cascade of electrons, and at the end we measure who came out first. So so first heavy elements and then light elements, and then we detect the M to Z ratio. According to this, we get, for instance, such mass spectrometer. This one is for the detecting rare earth elements. As we can see it here, we got a lot of rare earth elements, and this mass spectrometry method is really high resolutional method and sensitive, because, for instance, here around, as we said it, for instance, in the region of 3 or to 5 M to Z ratio, we got 3 elements, and we can see single peaks of each element, so separated peaks. We don't have the overlapping. On the other hand, of course, we can also measure the molecules, not only atoms. In this case, as I said it here, first we have to produce some vapor of the molecule, so of our sample. This vapor is then bombarded with electrons, and the molecule lost the electron, and we form the molecular positive ion, which already, and then those ions go to the mass spectrometer, we get the cascade, and at the end we measure M to Z ratios of the fragments, and on basis of those fragments that are formed during the ionizations, we can determine our final structure. So mass spectroscopy is usually used in combination. So for instance, with the gas chromatography, liquid chromatography, inductively coupled plasma mass spectrometry, or TG, thermogravimetric analyzers, so TGA-MS analyzers. So the third technique that is commonly used, there are separation techniques, and the most common are chromatography techniques. There are many other separation techniques, but as I said, for material characterization, we usually use chromatography. So first it was discovered or first mentioned or in 1903 by a Russian chemist and botanist Michael Twist. He first used the term of chromatography. He worked on the separation of the plant pigments, where he tested over 100 stationary phases and separated different plant pigments. But comparing to modern chromatography methods, the analysis take over several years. Now we do our analysis in maybe a few minutes, maximum couple of hours. And so chromatography methods, or basically the field, is very developed. So in this field, many Nobel Prizes were given over the years. So already from this part, we can see that this is quite powerful method for analyzing our materials. The chromatography is applied in all branches of science. It's separation method that is based on different interactions of compounds with two phases, so mobile phase and stationary phase. So when the mobile interaction, when the analyte is traveling with the mobile phase through the stationary phase, the compounds interact, and at the end we got the chromatogram that corresponds to the time of the analyte needed to pass through the system. So separation, detection, and determination of components in the mixtures based on its polarity, boiling point, ionic strength, also the size of the molecules. So I said it before, we got the different components or parts that are needed for chromatography. First is mobile phase. Here, this is the solvent that flows through the supporting medium. So in the mobile phase, we got also our analyte. Then we got the stationary phase. There's some layer of coating on the supporting medium that interact with the analyte. As the name said, it is stationary. Is positioned in the core of the chromatogram. Usually, this is some film. It's placed into the film in the column. Then we got the supporting medium. This is solid surface on which the stationary phase is bound or coated, and of course the analyte, the species that we need to detect quantitatively, analyze it or qualitatively. So all the chromatogram separation, so chromatography methods based on the sample is transported in the mobile phase, which could be gas, liquid, supercritical fluid. And this mobile phase is then forced through a immiscible stationary phase, which is fixed on the column on the solid surface. At this stage, interactions between the analyte and the stationary phase occur. And at the end, when our sample is eluted, we got the chromatogram. So this is again one basically the presentation how the chromatography works. If we see this strip as a stationary phase, here we got mobile phase with our analyte. It goes, it travel through the stationary phase because we got the difference at this stage two different molecules inside. Those molecules interact differently with our stationary phase, so we got more interaction with the blue phase, less with the red phase, and because of that, we got also different times needed for passing the analytes through the through our system. And on the basis of this, we got the chromatogram with two separated peaks. And on basis of that, we can quantitatively or qualitatively determine our analyte. So the chromatogram is basically the visual representation of the travel, of the velocity of travel of our analytes through the column, so to our system, and it's represented by the retention time. So the peaks are positioned at the certain time, which tells us what was the retention time of our analyte. So how much time it is needed to pass through the system. So this is the time between the injection of the and the maximum of the detector response for the analyte. It is inversely proportional to the eluent flow rate, and it's dedicated by the physics and chemistry. So, but by the chemistry, we got the station. We can get different retention times because of the interaction between the stationary phase and the analyte. Then the mobile phase, how is also the composition of mobile phase. Even the mobile phase can pass differently through the stationary phase. Then we can then is determined through the intermolecular forces and the temperature. And of course, the physics, how fast the mobile phase passes through the column dimensions, the pressure inside the system, and so on. So at the end, as I said, we got the peaks, and the peaks can be different. The perfect one should be symmetrical, so Gaussian shape of the peak, but in a real conditions we get also tailing or fronting, so not symmetrical peaks, and the peak width or the shape depend on numerous of parameters, so column length, flow rate, particle size. So also the depend on the interaction of the sample. How much sample do you have it inside? For instance, you don't want to overload our system. So because of this variation, usually the peaks should be represented as Gaussian, but with standard deviation, so plus minus, when we are putting out our results in a numerous form. So we know different, the chromatography methods are divided commonly in two sides, so gas chromatography and liquid chromatography. So gas chromatography, as the name said it, is chromatography technique that can be used to separate and analyze volatile organic compounds. So substances should be volatile without decomposition or are already in gaseous state, but they should be thermally stable up to 350 degrees. So the principles are the same as I presented you in the short introduction of chromatography, but with minor modification, because here we got the mobile phase is gas, and we got some modification due to the compressibility of the mobile phase. And also we have to choose the stationary phase wisely, because we need to know the chemical property of our analyte. So if it's polar, we should use polar stationary phase or vice versa. So gas chromatography is currently one of the most popular methods for separating and analyzing organic compounds. It's a really high resolution method with low detection limit, very fast, high accuracy, and very reproducible. So gas chromatography can be applied for analyzing the all the chemical products, separation of volatile mixtures. We can qualitatively or quantitatively analyze alcoholic beverages, food biomolecules. So everything that it can be put into the gaseous state, but is, as I said, it's stable up to a certain temperature. We know we can distinguish between two types of gas chromatography. So gas solid, here we got gas mobile phase and solid stationary phase. On the other side, we got gas liquid. Here we got liquid mobile phase. So liquid is immobilized on the surface of the inert solid inside the tube, so our column inside. So this, the second one, is most used one. The gas solid can be used for low molecular mass gaseous species. So simple gas chromatography system consists of the gas regulating system, injector of the sample, chromatographic column, which is the heart of the, or the core of the chromatography systems, then the detector, of course, and then the data system and display or computer. So on the other side, as I said, we got gas and then the liquid chromatography. As we can see it here, the types of liquid chromatography, we got different types of liquid chromatography, but mostly used is for material characterization is this column site. But today I will just talk about high pressure liquid chromatography. The basics for all of those sub chromatographies, so different kinds of chromatographies, is just how we use the stationary phase. So it's also quite a very wide used analytical method with high sensitivity, very high accurate quantitative determination. It's automated. we separate non-volatile and thermally fragile samples. We can use it for various substances, amino acids, block, nucleic acids, so on. We don't need a lot of high quantity of sample, and the preparation and purification of the sample is very easy. As I present you before, we got different types of high pressure liquid chromatography, and on this image we got representations, right? So if it's organic soluble or water soluble, and compared to the molar mass, which type of liquid chromatography we have to use. So if it's water soluble and ionic, usually used paired ion and ion exchange method. If we got hexane, so soluble only in organic solutions, we got normal phase or reverse phased methods. I would point out here that now liquid chromatography is basically HPLC. We always use HPLC method. Back in the future, we got liquid chromatography just to know which type of the chromatography we use it, but now most common one, the name is HPLC. So it's high performance or high pressure liquid chromatography. Both names are used. So as in all chromatographic methods, components of the mixture are partitioned between the stationary phase and the mobile phase. Stationary phase is adsorbed liquid, so that is absorbed on the very small particles. The particles are from 3 to 5 microns, or also depending on the analyte that we want to analyze, and the mobile phase is liquid. So compared to the comparison between HPLC and gas chromatography, there are so for gas chromatography, we always analyze volatile samples. In liquid chromatography, the sample has to be soluble in the mobile phase because the mobile phase is liquid. In both, we can separate and analyze polar and non-polar substances. So depending on the properties of our sample, we have to choose between gas chromatography or HPLC. But both of them, they are common methods for analyzing the samples, and they both got pros and cons. So as the gas chromatography system, also HPLC system is the same. So, but here we got the liquid mobile phases at the beginning, and in the gas chromatography, we got the gases and gas inlet system. Then we got the injection of the volume detector and completer. So the next method is the thermal methods. The most common one is the thermogravimetric method, or TG. You probably already heard. So here, this is the analysis method where mass of the sample is measured over the time as the temperature changes. So we measure mass versus temperature of the time. The TG is also one of the most accurate balances. With the position, the sample is positioned in the controlled atmosphere. We can measure it so in the normal atmosphere or reductive, oxidative, inert atmosphere. And then the plot of the mass or mass percentage as a function of time we get in the form of the thermogram, or we can use also the thermal decomposition curve. This is such instrument. Here inside we is a balance where we put our sample. It's isolated and also put it into the furnace. That the balance detect the change of the in the mass as the sample is heated up. So as we can see it here, we can get the representation or mass percentage versus time. So we got different time regimes and then different loss of the mass, or we got the mass percentage, mass versus temperature, so how we lose the mass during time, during the temperature. But however, we don't always lose the mass. The mass can also increase because sometimes we got some reactions or especially reductive or oxidative um, atmosphere, we can get that mass also can increase. So as I said, the source, the core of the TG instrument is thermal balance. We got different balances available now in the market. Mass range is from 1 milligram to 100 grams, but modern and high resolution TGs measure also from 1 to 100 milligrams. Sensitivity is 0.1 microgram. So a balance is housed in the furnace and is also thermally and vibrationally isolated from surrounding. Then the second part which is needed is the furnace. We got different furnaces, usually can heat up to 1,000 degrees. Some of TGs can go up to also 1,600 degrees. Heating range can be different from 0.1 to also 200 degrees. So we can have really small steps and can detect the difference in the mass really accurate. So it's also required that the interior is isolated and cooled so that we don't have any interferences from the surrounding or from heating of the components in the machine. But usually it's also combined with the mass spectrometer, so we can then also detect the product, so which are produced in the different stages of the thermal decomposition. So for the end, I would present you also the use of X-rays for the analysis of our materials. I think in a inorganic chemistry, so for synthesizing of inorganic materials, and nowadays also in some organic field, use of X-rays is very powerful methods to analyze our samples. So the outline is that first I will introduce you what are X-rays, then I will present you the two most common methods for material analysis. So this is EDXS, so energy dispersive X-ray spectrometry, and diffraction, so X-ray diffraction method. So here is our known image. We got different different spectrum, and our X-ray is so wavelength of X-ray corresponds in the range from 10 to 0.01 nanometers. We know soft and hard X-rays, so depending on the wavelength and energy. Mostly so common are hard X-rays. that we came across in our everyday life. For instance, if we travel a lot, or X-ray scanners are basically heart X-rays, and then medical CTs, mammographies, and of course then for X-ray crystallography. The X-ray is the same, so it's electromagnetic radiation. So the energy, and when it interacts with the sample, it interact in different ways. So we can get scattered X-rays, fluorescence, emissions, transmission, even heat. And depending what we observe it, we can get different information, and also different methods are used. So X-rays are usually generated in the X-ray tube. So this is some, as you imagine a bulb, where we got the filament, and this whole tube is under the high, it's vacuum sealed, and it uses high voltage to accelerate the electrons from the tungsten, for instance, tungsten filament. And then the electrons are released, and they bombarded and collide with high velocity with the metal target, which is anode, and the X-rays are created. So the maximum energy of produced X-rays photon is limited by energy of incident electrons, so voltage on the tube times electron charge. And for instance, 80 keV tube cannot create X-rays with energy greater than this value. So we need to also know what energy we need for different materials. So you can see the different anode materials can also produce different energies of X-rays. So as in the electromagnetic radiation, as I talked before here, when the electrons has enough energy to knock out the orbital electron from the inner electron shell, the X-rays are formed. So electron knocked out the inner electron, so the electron from the inner shell. The electron from higher energy level fill the vacancies, and so fill it, and the X-ray is emitted. And this we detected with the emission spectra of X-rays. We got different transitions. So from upper shells to core shells, we got the K lines, and then we got to the L shells, transitions in L shells, L lines. So this kind of the characteristics X-rays we usually use in our methods, the most common methods. So X-rays are the type of the electromagnetic wave. So they got duality, so dual nature. They can be waves and particles. So for when we use them as waves, we detect the diffraction phenomenon, so X or D method. When they are in particle behavior, we measure spectrometry, emission, and scattering. They've got the high power penetration, so can really pass through many types of materials, and they are electrically neutral, so they don't have neither plus or minus charge, and so they are not influenced by magnetic or electrical field. So first, really common method that use X-rays is energy dispersive X-ray spectroscopy. It's used for elemental analysis, so analyzing emitted X-rays produced by interaction of electrons beam with matter. It can be used for quantitative and qualitative analysis. Of course, the position of the, so energy The position of the peak at certain energy is meant for qualitative analysis, and intensity of the peak, so area below the peak, is meant for quantitative analysis. Advantages are that this method is non-destructive for our samples, got good accuracy and precision, can be done also on the particles. We can scan areas and get the information from the area, not just point, and we can do the multi-element analysis at the same time. But it's not suitable for light elements. Here we use the VDX methods of wavelength dispersive X-ray spectroscopy. We have to use expensive electronic microscope, and we need experienced staff to operate it and to analyze the results. So as I said, the principle is that when the element is placed in the electron beam, electrons are absorbed, so energy of electron is absorbed. At the beginning, atom is at the ground state, but incident beam excites the electrons in an inner shell, ejecting it from the shell and creating the electron hole. So electron hole is then filled with the electron from the higher energy, and the differences in the energy is released in the form of X-rays. Here we got this image is basically the EDXS spectrometer, which is placed in the scanning electron microscope. Here we got so some samples, what we can do it. As I said, it is very precise, and we can do it also on the nanoparticles, not point analysis, but also mapping. Here we got particles containing selenium, bismuth, chromium, and we can see it also so by the difference of the brightness, we can also detect where we got more of some elements and where less. For instance, in this part, we got less chromium. So in this upper part, we got more chromium. It can be meant for nanoparticle as well, of course, for micrometer samples, so bulk samples. Here is the one pellet. Basically, it's 1 millimeter big pellet. Here the window is around 100 nanometers. And also here we can see that we got mapping. Of course, we can do also point analysis. The result of the analysis is not just nice images of mapping, but also such a spectrogram where each element got its own energy, so we can really, by this energy, we can qualitatively detect which element we got it. So as I said, EDXS cannot be used for light elements. So because of that, we use wide wavelength dispersive X-ray spectroscopy. Basically, it's the same principles as in the EDXS, but we use here the wave. So we detect a single wavelength of the X-ray, not the broad spectrum of wavelengths or energies as in the EDXS analysis. The last one is the X-ray diffraction, another use of X-rays. Its most widely used is X-ray powder diffraction, but the same principles also apply for single crystals. It's used for identification of unknown materials based on their structure. We can identify fine-grained minerals, we determine their unit cell dimension, sample purity, and also we can qualitatively and quantitatively analyze the sample. The diffraction patterns are basically fingerprints of the material. So crystal structure of the solid will produce distinctive pattern of sharp peaks. On the other hand, if we got amorphous, we will just see some broad humps. For instance, here we can even detect the separate phases, so separate materials inside the mixture. For instance, if we got sample A, sample B mixed together, we can even distinguish between them. The principles lie on the Bragg's law. So the position of the diffraction peaks is determined by the distance between the planes of the atoms. Crystals are the arrays of atoms, and X-rays can be considered as electromagnetic radiation, so waves. So when the X-rays react or not react, come to the interact with our solid, they scatter in according to the Bragg's law. So the Bragg's law calculates the angle where the constructive interference from the X-rays, so incident X-ray, scatter by the parallel planes of the atoms, and therefore they produce the diffraction peak. According to this calculation, we get the diffractogram, which tells us the relation between the atomic planes and in the crystal and the angle of the incident wave. This is the powder diffraction of the alpha iron. So we got the diffraction peak, diffractions presented by the peaks for each crystal plane. So according to this, as I said, EDXS pattern is basically a fingerprint of our material. For instance, if this 200 plane will be little bit, so the crystal structure will be a little bit more be bigger or smaller. This 200, for instance, this 200 peak will be shifted a little bit. Of course, also all of other peaks. So strength of the X-ray powder diffraction is that it's very powerful and rapid. We can get really nice diffractogram below, so in 20 minutes, even faster. We need minimal sample preparation. So we just need some solid dry samples, put it in our sample folder and put it in the instrument. It's widely available, and basic data interpretation is relatively straightforward. Limitations is that for the easiest and best identification, we need homogeneous and single phase material. We have to have the access to the standard reference file of inorganic compounds. So we need to get the access to the library. Usually for good diffractogram, we need at least 1 gram of powder for the good resolution. Determination of the unit cell, indexing of the patterns for a non-isometric crystal system is very complicated. And in some cases, we can get also peak overlap, and therefore hard identification and determination of the purity. So as I said, each crystal structure, each material got its own structure, which is its own diffractogram, which is a fingerprint. Here is I would say the one simple explanation. So we got in the titanium dioxide can be in 3 different crystallographic structure: anatase, rutil, and briquette. You can buy random, so we can just buy titanium dioxide from the store. For instance, titanium dioxide is in the white color for our facade or walls. We don't know which crystal structure we got it inside. For sure, usually it is the anatase, but still we got tritol and brucite. We dried our sample, put it into XRD, and as you can see it, we can clearly identify our sample. Here we can see that we got all of 3 crystal structure of the TO2. For instance, we can also track the differences. So if we chemically change our sample, for instance, here with increasing the indium content in bismuth selenide, we can see it up to this 12 atomic percentage. The diffractograms are the same, but at 12 atomic percentage, we got additional peaks. So something happened with the sample. Also, we can track with changing the position of peaks if the crystal cell is changed its dimensions. This is commonly seen when we dope some material. Also, by the width of the XRD peak, we can see it if it's really highly crystalline or if it's in nano form and so on. So XRDs, with XRD, we can identify all of the phases, crystal phases. So from the peak position, from the D values, we can identify phase. We can get lattice parameters from the D shift, as I told you before. For instance, when we dope the sample, we can detect that we got the stress inside or solid solution detection. This is in the case of the metals. From the width of the peak, we can determine crystal quality, crystallite size, lattice distortions, even the intensity versus orientation. We can determine, for instance, in the magnetic samples, the degree of the orientation of the sample. So from XRD, we can basically really analyze our sample from through the whole range, basically. Also, here is again one representation of what we can do it. First we look peak list, so identified our sample from the database. Then we get lattice parameters, quantitative analysis, crystal size, lattice destruction, and with some methods, we can also define the crystallite size, the quantitative, so how much sample of each sample in our mixer we got it in our mixture. So this is one of the representation of the XRD. Here we got the sample X-ray tube, different slits, so we can define how big our So our light will be, so our beam, and on the other hand, other side we got the detectors. XRD, the instruments can come in basically tabletop version, then a little bit advanced versions, bigger, or even they can be placed inside the um, uh, synchrotrons, where we got really high intensity X-rays and more accurate analysis. So this was all from my side. So thank you for your attention. And if you got some questions, I'm open to it.
Thank you, Dr. Bele. We have few questions.
Yeah.
Let me. Hello, Priyam, can you hear me? I have unmuted you. You can ask your question.
Yes, sir. I can hear you. Am I audible right now?
Yes, yes, you are. You are very much clear. You can please proceed.
Okay. Sir, my question is that can we identify non-covalent bonding using FTIR?
So if we can detect non-covalent bonding,
Yes,
this
such
was
as
your question.
hydrogen bonding.
Yes, we can basically we know the vibration of the hydrogen bond, which it is. So this was the, for instance, if we measure the water molecules, so between two molecules of water.
Okay, sir, I have another question. Can we perform XRD analysis for non-crystalline materials as amorphous, or and can we detect the uh, element
So,
what it contains?
sorry, I didn't. It was a little bit distortion. So if we can use the XRD for non-crystalline.
Yes, yes. Is it possible?
Yes, if it's so we can measure it, but we will not get sharp peaks from it. We will get really broad peaks. Of course, some non-crystalline samples it will diffract. Of course, some sort of the crystallinity or symmetry inside the sample should be there. Of course, for instance, usually such non-crystalline samples diffract really broad peaks. So through the 20 to 32 theta degrees. But for certain XRD, it's not meant for the really non-crystalline samples. So amorphous samples we cannot. Something we will get out, but nothing that we can analyze it properly.
Okay, okay, sir. Thank you. Thank you for answering.
Yes, participants, if anybody else wants to ask question, they can raise their hand. We'll unmute you for a while. Or you can type your question in the chat box. Sir, I guess we don't have any other question from the participants.
Okay.
So we can, yes, yes. So we can close this session. Thank you very much, sir, for such a nice tutorial on the characterization of materials. I hope our participants have learned a lot from your lecture. With this, sir, we would like to close this session. Thank you, sir. Thank you for delivering your lecture, sir. Thank you.
Thank you
Participants. Okay.
thank you also for giving me opportunity to give the lecture.
Thank you. Thank you. Our pleasure, sir. Our pleasure. So participants, tomorrow we'll be meeting again at the same timing, and lecture 5 will be delivered by Professor Valant on the material properties and on the electrical properties of the materials. So till then, a very goodbye. Thank you. Thank you for joining. Thank you, sir.